Hi, welcome to the Learning Zone. This is Mr. B. In this video, I will explain how to perform calculations using the combined gas law. The combined gas law is actually a combination of three different gas laws: Boyle's law, Charles's law, and Gay-Lussac's law. According to Boyle's law, the volume and the pressure of a gas are inversely proportional, and this graph represents the relationship between volume and pressure according to Boyle's law. Charles's law states that the volume and the Kelvin temperature of a gas are directly proportional, and this graph represents the relationship between volume and Kelvin temperature according to Charles's law. Gay-Lussac's law states that the pressure and the Kelvin temperature of a gas are directly proportional, and this graph represents the relationship between pressure and Kelvin temperature according to Gay-Lussac's law. When performing gas law calculations, the Kelvin temperature scale should always be used. This graph represents the relationship between the volume of a gas versus its Kelvin temperature. Notice that as the temperature decreases, the volume will also decrease proportionally. At a certain point, the temperature may no longer be physically decreased. However, since the slope of the line is clearly 1, the plot may be extrapolated to the x-axis. This point represents negative 273 degrees Celsius, or 0 degrees Kelvin. 0 degrees Kelvin is also known as absolute zero, and at absolute zero, no particle motion will occur. This means that the volume of the gas will be 0, and the pressure will also be 0. Therefore, 0 degrees K should never appear in a gas law calculation. 0 degrees Kelvin, or absolute zero, is a theoretical temperature that is thermodynamically impossible to achieve. For a particular sample of a gas, the combined gas law states that the initial pressure times the initial volume divided by the initial temperature will equal the final pressure times the final volume divided by the final temperature. Or we may write P1 V1 divided by T1 is equal to P2 V2 divided by T2. When using the combined gas law, it is always convenient to simplify. To simplify the combined gas law, multiply through by T1 T2. The simplified version of the combined gas law will then be written as follows: T2 P1 V1 is equal to T1 P2 V2. Now let's apply the combined gas law to a few practice problems. Consider the following. Calculate the new volume of a gas if the initial volume was 2.0 liters at a pressure of 0.50 atmospheres, and the pressure increases to 2.0 atmospheres, assuming no change in temperature. From the modified version of the combined gas law, where T2 P1 V1 is equal to T1 P2 V2, we may eliminate the T's. Clearly in the information, the temperature remains unchanged. Therefore, the combined gas law is simplified as follows, where P1 V1 is equal to P2 V2. This represents Boyle's law. From the information, V1 is equal to 2.0 liters, and P1 is equal to 0.50 atmospheres, and P2 is equal to 2.0 atmospheres. Now we rearrange the formula to solve for V2, where V2 is equal to V1 times P1 over P2. Inserting the data will yield the following, where V2 is equal to 2.0 liters times 0.50 atmospheres divided by 2.0 atmospheres. After canceling the units, V2 will equal 0.5 liters, or 500 milliliters. Now let's use the combined gas law to calculate the new temperature of a gas. Consider the following. Calculate the new temperature of a gas. If the volume decreases from 50 liters at 25 degrees Celsius to 0.50 liters, assuming no change in pressure. Since the pressure remains the same, the P's in the combined gas law may be eliminated. This results in the following, where T2V1 is equal to T1V2. This represents Charles' law. From the information, the temperature is given as 25 degrees Celsius. However, when performing gas law calculations, the Kelvin scale should always be used. To convert the Celsius temperature to Kelvin temperature, we simply add 273. This will give a Kelvin temperature of 298 K. Now we rearrange the formula to solve for T2. T2 will equal T1 times V2 divided by V1. Now we insert the information, and T2 will equal 298 K times 0.5 liter divided by 50 liters. And T2 will equal 2.98 K. Now let's use the combined gas law directly to determine the new pressure of a gas. Consider the following example. A certain gas occupies a volume of 0.15 liter at a pressure of 101.3 kPa and a temperature of 303 K. Calculate the new pressure of the gas if the temperature changes to 95 degrees Celsius and the volume increases to 300 milliliters. The first step is to perform a few conversions. 0.15 liter is equal to 150 milliliters. 101.3 kPa is equal to 1 atmosphere, and 95 degrees Celsius is equal to 368 K. Now we rearrange the combined gas law to solve for P2. P2 is equal to P1 times T2 times V1 divided by T1 times V2. Inserting the information, P2 will equal 1 atmosphere times 368 K divided by 303 K times 150 milliliters divided by 300 milliliters. At this point, the units will cancel, and P2 will equal 1 atmosphere times 1.21 times 0.50, and P2 will equal 0.61 atmosphere, which will also equal 61.8 kPa, or 463.6 millimeters of mercury. It is important to remember that the combined gas law applies to an ideal gas. In addition, when performing gas law calculations, always use common units and always use Kelvin temperature. This concludes my explanation of how to perform calculations using the combined gas law. Hopefully this video has been helpful. Thanks for watching.